Hello there, CSEC chemistry students. Let's work through a specimen paper 1 from CXC. So this was from the year 2012. And so just a few instructions, as you might be well aware of. There are 60 items on this paper 1. You will have about an hour and 15 minutes to answer them. And so that gives you roughly a minute and some change per question, okay? All right, so moving right along, let's get into it. So here is our questions 1 to 2. So it says items 1 to 2 refer to the table below, which presents 2 physical properties of 4 substances at room temperature, right? In answering the items, each of the options below may be used once or not at all, okay? All right. So let's look at this now. So we have our substances here, our 4 substances, P, Q, R, and S. We have the melting point of all of these substances, and we have boiling point, right? So A would represent an answer that's only P, B would represent an answer that's only R, and then C would be what? P and S, and then Q and R only, okay? So we can use the options once or not at all, right? Okay, so the first question is saying which substance will have fast moving particles, right? So if a substance has fast moving particles, that means that it's fairly, the bonds between the molecules aren't as strong, right? So the particles can move very rapidly. And so that would indicate something that's in a gaseous state or something that's in a liquid state when compared to other states, right? So let's look at our melting point and our boiling point. And we see here that P has a particularly low melting point and a low boiling point when compared to all these other substances. So that would indicate that in P, the bonds are very weak, right? So it's easy to boil it, to change that state. And it's easy to melt it because those bonds aren't as strong. And so when we compare this P to all the other ones, we see that it's tremendously much lower than all the others in terms of its melting point and boiling point. And so our answer for 1 will be A, right? So all we're doing is relating the structure and bonding information that we're given from the melting point and then relate that to the speed of the molecules, right? All right. So question 2 says, which one of these substances will be a solid? Now, in solids, we know that the particles are closely packed together and the bonds are strong, right? And so it will be hard to break them apart. So we're looking for a substance up here that has a high melting point and also a high boiling point. So that could very well be Q. Q is the highest melting point and the highest boiling point. So Q is definitely in our answer, right? And because we don't have any Q by itself, we know right away that R has to go with it, right? So Q and R will be our answer for 2. So that's D. Okay, so 2 is D. And so we're moving right along. So again, that's a solid because we see that it has a very high melting point. Both Q and R, high melting point, high boiling point. So that's a solid. Answer is D. Okay? So moving on to question 3. Question 3 says that at a stage in the process of extracting sucrose from sugarcane, lime is added to the sucrose solution. So remember what lime is now. Lime, let's just make that clear that that's calcium hydroxide, right? So when we're doing the extraction of sucrose from sugarcane and we add lime to the sucrose solution, why are we adding it? Are we adding it to lower the pH of the solution? Are we adding it to raise the pH of the solution? Are we adding it to stop the sucrose from changing into sugars? Or are we adding lime to increase the percentage of sugar that would crystallize out? Well, again, if you jog back your memory to this section of the syllabus, essentially what we're doing is we're adding the calcium hydroxide, which is a base, because the sucrose that we get from sugarcane is slightly acidic in nature. So it's a slightly acidic green suspension that we're going to get from this step. And so if we have an acid, then why would we be adding a base to it? We're adding a base so we can neutralize it, right? And effectively what we're going to end up doing is raising the pH, right? So we're going to be raising the pH because we add the base and bases have a higher pH. So we're going to raise the pH from the low acidic pH to a higher pH. So what we're doing is B here. So we are raising the pH of the solution, okay? So the answer here is B. So that's that. And let's see. Yeah, so that's that, right? So let's move on to question 4, right? So question 4 says that a mixture of copper 2 chloride solution and copper 2 oxide could be best separated how? So how are we going to be best able to separate copper 2 chloride, right, from copper 2 oxide? So when we're doing these separations, what we have to know or to think of immediately is the relative solubility of these two compounds that are in the mixture, okay? So we have copper 2 chloride and we have copper 2 oxide. Now we know that copper 2 oxide is an insoluble oxide, right? So that's insoluble in water. So it's not going to be soluble in water. So the best way that we can separate this is if we add water to the mixture and just shake. And what's going to happen is that because the copper 2 oxide is insoluble in water, it's going to precipitate out. And so we're gonna be able to then filter off the copper chloride, right? So the answer here would be C. So we're gonna shake the mixture with excess water. The copper 2 oxide is insoluble, so it's gonna precipitate out, and then we just filter off the remainder. And when we filter that, now we'll be able to get copper chloride in one container, and then we'll have our copper oxide remaining as a precipitate. Okay. All right. So question 5 now says, which of the following halogens is a liquid at room temperature? Halogens, liquid at room temperature. You might remember that as you go down the group, as you go down that group 7 where the halogens are, we're going from gas. So the fluorine is a gas, chlorine is a gas, and then bromine will be a liquid, and then iodine will be a solid, right? So if we're gonna choose which one is liquid at room temperature, of course it's gonna be bromine. So our answer is A. So the key here is just to remember some trends in halogens. As you go down the group, your physical state changes from gas to solid. Okay? All right, so bromine is our answer for 5, so that's A. And then moving along to question 6. Question 6 says, which of the following compounds does not consist of individual molecules, right? So remember what molecules are, how we define that. Molecules are of more than one atoms in them, right? More than one atoms. So which one of these doesn't have more than one atoms, right? Is really what it's asking you. We know ethane, the formula is this is C2H6. It has a ton of atoms, so it's not this one. This one does have individual molecules. So this has individual molecules. Ethanol, this is our formula for ethanol here, C2H5OH. It does have individual molecules. And then hydrogen chloride also has individual molecules. It's a covalent structure, right? Made up of 2 different atoms, and then those come together to form a molecule, right? And now when we look at sodium chloride, which is NaCl, we might remember that actually what it is Na plus, the ion form of it, right? This is ionic bonding. So it's a sodium ion and the chloride ion that are coming together. So these are not atoms, and so this is not going to be made up of individual molecules, okay? It's made up of individual ions of sodium ions and chloride ions that are arranged in a lattice structure. So that's how we land on D for answer for 6, right? Remember now, you have to think of the bonding and the structure of these compounds, and these are all molecular compounds, whereas this is an ionic compound, and so it will just be sodium chloride, right? So that's our answer there for 6, that's D. And so we're moving on to question 7. Question 7 says, which of the following salts are soluble in water? So we have to jog our memory now. So let's look at the salts that they give us. They gave us a carbonate, a sulfate, and a nitrate, right? So follow me over here where I have just a little revision on the solubility of different salts, right? So carbonates are all insoluble in water, except if it's a carbonate that's made up of potassium, sodium, or the ammonium ion, right? So all carbonates are insoluble, right? So we know that this is going to be insoluble. Well, no, this would be soluble because it's made up of ammonium. So this would be soluble. So let's leave that there. Ammonium carbonate would be soluble, right? Because it's an exception to that rule that carbonates are insoluble. So we have ammonium carbonate, that would be soluble. So let's write S beside that. That's soluble, right? So now when we look at sulfates, let's look at barium sulfate. We know that all sulfates are soluble except, right? Except lead, barium, and then calcium sulfate is only slightly soluble, right? So they're asking which of these are going to be soluble in water. We know that barium sulfate will not be, right? So this is insoluble because it's one of those exceptions to that sulfate rule, right? All sulfates are soluble except barium, lead, and that calcium there. So ammonium carbonate is soluble, barium sulfate is insoluble, and lead nitrate. Now let's look at nitrate. Nitrates, all nitrates are soluble. So this one is going to be soluble in water. So our only insoluble one is what? Only insoluble one is barium sulfate, and the question is asking us about which ones are soluble. So those would be what? 1 and 3, okay? So that would be B. So 7 is B. So just make sure that you remember this little these notes here, right? Carbonates insoluble except these ones. Sulfates are all soluble except these ones, and nitrates are all soluble in water. Okay? So the answer for 7 again is B. Okay? Okay, so moving right along to question 8. So question 8 says that in the ionic equation between zinc and sulfuric acid can be best represented by which of these equations are ionic equations, right? So the key thing to remember here is that in an ionic equation, there should be no spectator ions. And what we mean by spectator ions is like ions that don't change their charge from when they move from the reactant side to the product side. They're literally in the exact same oxidation state. If that's the case, they're spectators, and if any equation has in those spectators, it cannot be an ionic equation, okay? So we're looking for the equations here that have no spectator ions. So if we look at the very first one, we see that zinc over here is 0, and over the product side it's 2+, so that oxidation state changed, right? We see that hydrogen over here is in the +1 state, but over here it's uncombined, so it's 0. So this one could work, right? No spectators there, nobody just hanging around without a change of state. So this one can work. Let's look at B though. B has zinc is in that 0 state, it's uncombined. Over here it's +2 though, and then the sulfate beside it would be -2. The hydrogen is 0 because it's uncombined. The hydrogen is plus over here, but the sulfate is -2. So because the sulfate didn't change state from -2 as it changed from reactant to product, we're going to cancel. This one is not going to work, right? Because we have these spectators here. Let's see if we have any spectators down here. 0 for zinc over here, +2 over here, plus for hydrogen over here, 0 for hydrogen over here. And then the sulfate is -2 over here, and then the sulfate is -2 over here. So that didn't change. It's still spectating, and we can't have any spectators in our ionic equation. So this one wouldn't work. Let's look at this one. Zinc is 0 over here. It's 2+ over here. So that changed state. Hydrogen is plus over here. It's 0 over here. So that one changed state. Now the sulfate is 2- here, and it's still 2- here. So that didn't change state. So we can't use that one. So our answer is A, right, guys? A is the only one that doesn't have any spectators. So that's our ionic equation. Okay? So 8 is A. Moving along to 9 now. 9 says, in which of the following compounds does manganese have an oxidation number of +7? Right? So we're looking for the one of these compounds in which manganese has an oxidation state of +7. Now the key thing to remember here, or to notice here, is that all of these compounds are neutral compounds, right? So that means that whenever I add up the oxidation number of, say, manganese and oxygen, I should end up getting 0, right? So I know oxygen is normally -2, so that means that the Mn has to be +2 in this particular case, right? So that's not 7, and 7 is what we're looking for. Let's look at this one now. Also a neutral compound. The oxidation state of the oxygen is -2, and there are 2 of them. So overall, that's -4. When I add it to +4, that's when I'm going to get 0. So my oxidation state of manganese in this is +4. That's not what we're looking for. In this particular case, again, no, okay, oxygen has an oxidation state of -2 in this compound. So that's overall, what's that, -6. So I have to have the Mn being +3 in this particular compound for the overall thing to add up to 0. So this is not what we're looking for. And then if we look at D now, oxygen is -2 in this state. There are 4 of them, so the whole of this comes up to 8, right? And then we know potassium is +1 in every compound that it's in. And then we can finally solve for the Mn, right? So this is -8, by the way. So 4 times -2 -8. The K is +1, and we want to find Mn, right? Again, I said all of these numbers have to add up to 0, so that would leave us with a Mn of +7, having to be +7, okay? So +7 + 1 give us 8, 8 minus 8, 0. So our answer here is D, right? This is the one where we have a +7 oxidation state, and that's what the question is asking us about. So these are answer for 9, okay? So moving down to question 10 now, it says items 10 to 12 refer to the following information. So they're giving us some information here to then ask us some questions on. So a compound, when treated with aqueous sodium hydroxide, so that's NaOH aqueous, right? When we treat a compound, so say the compound is X, when we treat that compound with sodium hydroxide, we're gonna get a gas that turns moist red litmus paper blue, right? So it's a colorless gas that turns moist red litmus paper blue. So anything that turns red litmus paper blue has to be a basic or alkaline substance, right? And they told us it's a gas, so we know we're gonna get an alkaline gas, right? So let's look among our answers now. We say the gas given off is, we're looking for an alkaline gas, guys. And right away, we see ammonia. Ammonia is in fact an alkaline gas. So ammonia is our answer here. But if we were to look at these other ones, sulfur dioxide, nitrogen dioxide, and hydrogen sulfide, these are all acidic gases. So those could not be right? These could not be our answer because they're all acidic gases. And we know based on how the litmus paper changed from red to blue that we have an alkaline gas. So our answer for 10 has to be A, okay? Because that's ammonia, which is an alkaline gas. All right? So that's 10. So moving along to question 11. Question 11 says that the aqueous sodium hydroxide, in this case up here, where it reacts with the compound that we don't know to give us this ammonia gas, what is the aqueous sodium hydroxide acting as? Is it acting as a base? Is it acting as an acid, a catalyst, or a reducing agent? Well, we know that more often than not, aqueous sodium hydroxide is going to act as a base, right? So we're going to put base for 11. We know that aqueous sodium hydroxide is a very strong base, so it's going to be utilizing its basic properties here to give us the ammonia. So 11 is A, right? So moving down to 12, 12 says that the compound, so this X or unknown, what is it most likely? Right? It's most likely which compound is from this is gonna give us an ammonia as gas. There's nowhere from here for ammonia to come from when we react that with our strong base, right? So this is not it. Would sodium nitrate give us ammonia when we react it with sodium hydroxide? No, there's nowhere for the ammonia to come from, right? But if we look at ammonium nitrate, right, which is NH4 NO3, we can get ammonia from out of here, right? We can get NH3 from out of that. So right away, we know that C has to be our answer here for our starting compound that we're going to react the NaOH with, right? Aluminum hydroxide, same thing. There's nowhere out of that to get ammonia gas when we react that with NaOH. So this is not our answer, right? Our answer is C. And so the actual equation, guys, for that reaction, if you were interested, is that we're going to have the ammonium nitrate, which is our unknown compound X from up here, right? If that compound react with the strong base, sodium hydroxide, then we're going to get ammonia, we're going to get sodium nitrate salt, and we're going to get water. So that's actually how we create or produce ammonia gas in the lab. We're going to have an ammonium salt, reacting that with a strong base, and we get ammonia, a salt, and water. Okay, so this is our actual reaction, and so we know that our answer is indeed has to be an ammonium salt, which is ammonium nitrate in this case. So that's C. Okay, hope that makes sense. So that's 12C. So moving down to 13, 13 says, which of the following can act as an oxidizing agent, right? So right away we have to think, okay, how do we define oxidizing agents again? Well, oxidizing agents oxidize other substances while they themselves get reduced, right? So remember now, reduction is what? Reduction is gain, right? So when we look at these species, we have to say, okay, the species that can gain electrons are gonna be our good oxidizing agents, because if they can gain electrons, that means that they can, cause other substances to lose that, aka oxidize them, make them lose their electrons so that they can then grab them and gain them, thereby being reduced themselves. So if we have a metal ion, so say we have Na plus, so we have a metallic atom, which is just Na, that's neutral. And so we have non-metallic atoms, like say a chlorine, right? So remember, you have to pay attention to these actual particles. It's an ion, so we know it has a charge. Atom, so we know it's neutral. Atom again, neutral atom, right? So which of these is gonna be able to attract an electron to itself? Right away, we can send this metallic ion will do that, right? Because it had lost something, so it has to gain it back to become neutral. So this can act as a powerful oxidizing agent, metallic ions. Will metallic atoms act as a powerful oxidizing agent? No, because metal atoms are more likely to lose than they are to gain, right? So this can't work. Let's look at non-metallic atoms now, like a chlorine, right? When chlorine forms an ion, it's actually gaining an electron to form Cl minus. So we know that these are good gainers of electrons as well. So this can work. So this can work too. So our answers for 13 then will be what? 1 and 3. So that will be C. Right? Metallic atoms cannot act as good oxidizing agents because they naturally want to lose electrons and not gain them. So they're not going to be reduced readily. Okay? So our answer is for 13 is C, and we are moving right along to 14. So 14 says that in the electrolysis of copper 2 chloride, right, solution, we're using carbon electrodes, and you might remember that carbon electrodes are what? These are inert, right? So they're not gonna affect the what gets discharged at the electrodes. So we're using carbon electrodes, which are inert, and we're electrolyzing copper 2 chloride. So that's CuCl2. That's an ionic compound that's made up of Cu2 plus ions and Cl minus ions, right? So the substance that's gonna form at the anode is anode. So we know that at the anode, what go towards the anode? Anions are going to go towards the anode, right? And in this compound here, our anion is Cl minus. So Cl minus is going to go to the anode. And remember now, at the anode, oxidation takes place. So it's going to get oxidized, right? It's going to get oxidized at the anode. Once it goes there, the chloride ion. And remember, we said what? Oxidation is the loss of electrons. So it's going to lose the excess electrons that it had, and it's going to go back to being just chlorine. So our answer here is chlorine, okay? So we're going to get chlorine gas being formed at the anode because our chloride anion is going to go towards the anode. It's going to get oxidized, meaning it's going to lose every excess electrons, and it's going to go back to just being chlorine gas, that neutral gas, okay? So 14 is D. Okay, so moving along to 15. 15 says, which of the following substances will not conduct electricity? Not conduct electricity. It's a non-conductor. Right away, we have to think of what do we need for conduction. Before we even look at our answers, we say, what do we need for conduction? We need either mobile ions or we need electrons for conduction. Mobile ions or electrons. So ions that can move or electrons that can move. That's what we need for conduction. So when we look here, we're looking for things that don't have these properties, that doesn't have mobile electrons or ions, right? So if we have solid calcium, we know that that's a metal, and in metallic bonding we have what? We have some positive ions, right? in a sea of delocalized electrons, right? So that's what we have in metallic bonding, and solid calcium is a metal. So this one will be able to conduct. Molten calcium is just gonna be what? That's essentially liquid calcium. So it's still gonna have the metallic bonding present, but now it's like more molten, so even freer. These positive ions in the sea of electrons are gonna be even freer in this molten state. So this will conduct as well. Now, if we have solid calcium chloride, right? So we have calcium chloride, so CaCl2, and that's solid. This is an ionic compound, and effectively what's happening is that the calcium ion and the chloride ions that would ordinarily be free if it wasn't in a solid state are gonna kind of be frozen in place. So these ions that make up the calcium chloride are not gonna be free to move when they're in the solid state. And so this is not gonna be able to conduct electricity, okay? So right away we can stop here and say our answer has to be C. It's not gonna conduct because the ions are frozen in place. So let's just write that down. So frozen ions pretty much. So they're not mobile, and we need mobile ions for conduction. So this one is not going to conduct, right? And now if we look at D says that a solution of calcium chloride in water, that's for sure will conduct, right? Because now the ions are free to move. They're in water. They're free to move about. They're not frozen in place, right? So we know that this one would conduct as well. So the only one, again, goes back to C. Solid calcium chloride will not conduct. So our answer for 15 is C. Okay? All right, so moving down to 16 now. 16 says, which of the following statements about isotopes is not true? Right? Which of the following statements about isotopes is not true? Right? Isotopes, diseases can be diagnosed and treated using isotopes. That's true, right? This is true because we know that we treat like thyroid diseases, cancer, and all these different things using radioisotopes or radiotherapy, right? B says the age of archaeological specimens can be determined using carbon-12 dating. That's actually not true. That's not true because we do dating using carbon-14, not carbon-12. So this is not true about isotopes. We're gonna use isotopes in dating, you know, guys, but we're gonna use the carbon-14 form and not the carbon-12. Okay, so this is an incorrect statement. So C says that in artificial pacemakers, plutonium-238 is used in thermoelectric batteries, and we know that this is true, right? And then for D, you know, nuclear power stations use the fission of uranium-235 as a source of energy. We know that to be true, right? So again, what's not true here is this statement in B, which is saying that we're using carbon-12 for dating. We are not. We're using carbon-14, okay? This is what we're using. Okay, guys, this is what we use for dating to find out the age of fossils, okay? So B is our answer for 16. And so we're moving down to 17. 17 says, which of the properties below will decrease as you go down the group, as you go down group 7, right? So we're going this way. We're going from fluorine, chlorine, bromine down to iodine. Which of these properties will decrease as you go down the group? Let's think about atomic radius. Let's talk about this one. As we go down the group, you know that more shells are being added, right? So the atomic radius is actually going to increase as you go down the group, right? Electronegativity, as it relates to the elements in group 7, we know that the ones at the top are most electronegative. So the electronegativity is actually going to decrease as you go down the group, because the one up here is more, remember that most electronegative is up here, and then least electronegative is down at the bottom of the group, right? So we know that that's something that's going to decrease as you go down the group, right? Oxidizing power, this one is the most powerful oxidizing agent. F2 is the most powerful oxidizing agent, right? And so this one down here will be the least powerful oxidizing agent, right? And so this also decreases as you go down the group. So our answer here has to be one that has 2 and 3. So that is C. So C is our answer for 17, okay? So this is just remembering your trends in group 7, okay? All right, so we're moving on to question 18 now. Question 18 says that the layer-like arrangement of graphite and the weak bonds between the layers that determine graphite, between the layers determine that graphite is. So how does this affect the properties that we see in graphite, right? The hexagonal layers that we have. It determines that graphite is graphite colorless and transmit light? No, that's not true. Is graphite very hard with a high density? No, that's not true. Is graphite greasy and can be used as a lubricant? Yes, this is true. So our answer here is C, okay? So that those weak bonds are what give us those properties. So we're relating the structure to the function, right? So the structure here is that it has weak bonds in between these layers, these layer-like arrangement. So structure to function or property is what we're doing here. So if something has weak bonds in between it, we're gonna be able to like slide over the layers, we're gonna slide over each other fairly easily. So that's gonna be greasy and can be used as a lubricant, right? No. Look, if we look at D, some people might get tripped up by option D, but don't. Yes, graphite is a good conductor of electricity, but that has to do more with the free electrons, right? This has to do more with there being mobile electrons, and that's not the property that they're stating up here. They're stating about the layer-like arrangement and the weak bonds, and that's what give rise to the greasiness and its property as a lubricant, okay? So make sure that you're at all times you're relating the structure that they give you to what the specific function will be, and don't go outside of that, right? So our answer here is 18. For 18 is C, okay? All right, so moving along to 19. 19 says, which of the following copper 2 compounds is least suitable for preparing copper 2 sulfate by reacting with dilute sulfuric acid? All right, so we're preparing copper 2 sulfate. That's what we're trying to prepare. And that's a soluble salt, right? So whenever we're preparing soluble salts, what we want to do, like a soluble salt like copper 2 sulfate, right? What we want to do is we're going to want to use an insoluble base and an acid, right? So our acid here obviously is dilute sulfuric acid that we're using. So then what else would we need? An insoluble base, right? Oxide is an insoluble base, right? So this would be suitable to use. Chloride is not, and it's actually a soluble base, right? So we can't use this. Carbonates are insoluble bases, so we could use that and be okay. Hydroxide we could use and also be okay because it's an insoluble base. So the only thing here that's not in an insoluble base is chloride. So we're not going to want to use chloride, right? And remember, they're asking us about the least suitable. So the chloride is not suitable at all because we want an insoluble base to react with our acid because we're forming a soluble salt, okay? All right, so our answer for 19 is going to be B, okay? So moving along to 20 now. 20 says, which of the following statements would be correct if diamond and graphite are allotropes, right? So right away, we have to drag our memories back to how we define allotropes, right? So allotropes, these are different structural forms of the exact same element, right? So diamond and graphite are different structural forms of carbon. They're both carbon, but carbon in a different structure, right? So both of them can then be represented as a symbol C. So this would be true, right? Because they're both made up of carbon, but just have different structures, right? They're gonna both have a relative atomic mass equal to that of carbon. That's true because they're both made of carbon, okay? No. Part 3 says they have similar chemical properties. That's not true. They're not gonna have similar chemical properties because they have different structural forms, right? So if they have different structural forms, it means that their bonding is gonna be different, right? The structure and bonding in them is gonna be different between diamond and graphite, and we know that that's true. They have different structure and bonding, and so they're gonna have different physical properties. We know that diamond is hard. We know that graphite is soft and greasy, right? We know that diamond doesn't conduct, and we know that graphite conducts. Those are all physical properties that come from the structure and bonding, right? And the fact that they're different, right? So they're not gonna have similar physical properties. In fact, they're gonna have different physical properties. And so this 3 is not correct, but all the others are correct. And so our answer for 20 will be 1 and 2, so that's A. Okay? All right, so moving right along now to 21. 21 says, which of the following bonds can be formed by an atom of hydrogen? Right? So what kind of bonding do we have that are possible with hydrogen? Can we form an ionic bond by hydrogen atom losing an electron? Yeah, and that would be H plus, right? And that's very common in when we have like acids being ionized or anything of that nature, right? So we can form an ionic bond that way. An ionic bond by gaining an electron. So if the hydrogen gains an electron, it would end up being what? H minus. And we have H minus in compounds like sodium hydride. So this is a possibility, right? So this can form an ionic bond. This can form an ionic bond by gaining. So we can get compounds like this. And then finally, a covalent bond can be formed by a hydrogen atom by sharing a pair of electrons. And that's exactly what we see in this case where we have our diatomic hydrogen gas, right? So that's correct. That's correct as well. So all of these, hydrogen can exist in all these different oxidation states. So in this state, it would be 0, then it's -1 here, and it's +1 here. So all of these are possible answers of how we can form bonds using hydrogen. So our answer for 21 then is going to be D. Okay? All right, so moving along to 22. 22 says, this says item 22 refers to 24 refers to the following energy profile diagram, right? So in our energy profile diagram, we're seeing our energy of the reactants, energy of our products, and we're having the reaction pathway here that just shows us going from reactants to products, okay? So let's just orient ourselves as to what an energy profile diagram is first of all and what it's showing us, right? So they're asking us now which letter in the diagram denotes the energy necessary, right, for the reaction to take place. So what's absolutely necessary for a reaction to take place is the activation energy, right? So we need to have that, at least that activation energy to overcome this barrier so that we can go from reactants. So let me just write that our reactants are over here, right? In order to go from reactants over to our products over here, we need to overcome the activation energy, which is generally this hump that we see in the energy profile diagram. So we need to overcome this hump right here. And so that's what? That's represented by M, the arrow M, right? So we need to overcome M if we're going to then be able to form products. So our answer for 22 is B. Okay? All right, so moving on to 23 now. 23 says, which of the following equations is correct for delta H, or the enthalpy change, right? So enthalpy change, we know, is the delta H, or the H of our products minus the H of our reactants, right? So the H of our products is actually P. It's given by this here, this section here. So that's P. So H of our products, right, is given by P, and then minus the H of our reactants. That's what's going to give us our delta H. And the H of our reactant is given by this section here. So that's going to be L, right? So that's L. So P minus L is going to give us our delta H. Remember now, delta H is the H of your products, or the energy content of your products, minus the energy content of your reactants. And in this case, that's P minus L. So we look for P minus L among our answers, and it turns out that that's A. So our answer for 23 is A. Okay? So moving on to 24. 24 says, which of the following statements about the forward reaction is not true? So let's look at our forward reaction. Our forward reaction is we're going from reactants at this energy, this amount of energy, and we go up, overcome this activation energy, and we come down and we have products, right? The products are at a lower energy than the reactants. And so what is this energy profile diagram characteristic of? That's a forward reaction, right? And it's characteristic of an exothermic reaction, right? So this is for an exothermic reaction. Exothermic reaction. And we know that because the energy of our products is less than the energy of our reactants, okay? All right, and that's our forward reaction. So let's see what they're saying here, which is not true about the forward reaction. the forward reaction, delta H is going to be negative. This is true because it's an exothermic reaction, as we just said, right? So delta H is negative for exothermic reaction. This is an exothermic reaction, so we know that this first statement is true. The reaction is exothermic. Yes, we just said that, so that's true. Remember, we're looking for what's not true, right? So these two things are true, right? The energy content of the product is greater than that of the reactants. That's not true. And we can tell that by even just looking at the graph. The energy content of the reactant is greater than that of the product. So see, energy content of the product is greater. No, so that's not true. Energy content of the product is less. And because it's less, it's exothermic, as we said in these previous steps, okay? The energy necessary for the reverse reaction is greater than the forward reaction. That's true. That's true. So the answer here, what's not true, is C. C is not true, right? Because we have an exothermic reaction. So C is not true, and so 24 is C. Okay? So moving along to question 25 now. So 25 says, which of the following diagrams best describes bonding or illustrates bonding in nitrogen? Now, we know that nitrogen is going to form a triple bond with itself, right? So we're going to look for the bonding here that shows triple bonding with itself. And so it's not this one, because this would represent an NN, just a single bond. This one would represent an N double bond N, because there are two pairs of electrons in it. So that would be 1, 2, and this is 1. And then in this case, we see that we have what? 1, 2, 3 pairs of electrons. So that's a triple bond N, triple bond N. And then down here, we see that we have an N single bond end again. So in this particular case, then, I guess, as we said, nitrogen bonds with itself in a triple bond form. So the answer for 25 is C. That's what we're looking for from the jump, okay? Okay, so 25 is C. Moving along to 26. 26 says oxygen 1680 occurs before neon, which is 2010 Ne. In the periodic table, because oxygen, what about oxygen? Is it better oxidizing than neon? No, that's not how we arrange our periodic table. We're going to arrange our periodic table based on number of protons, right? So the way that we arrange a periodic table has nothing to do with oxidizing agents or so on. It's based on the arrangement of the periodic table, is based on the number of protons in an atom, okay? So A is not correct. Did we arrange it so because oxygen has fewer protons in its atom than neutron? Yeah, we can see that here. So this has 8 protons and this has 10 protons. So that's why we arrange it the way that we arrange it, right? Remember now, periodic table is an arrangement based on number of protons. So B is our answer here, okay? All right, so 26 is B. So moving along to 27. So items 27 to 30 refer to the following information. It says that a piece of calcium is added to some distilled water in a container, and the following observations are recorded, right? So what we see is that the reaction is rapid, right? We see that there's a bubble of gas that gets evolved, and we also see that there's a white suspension that gets formed, right? And so we also see a temperature increase, right? And when we see a temperature increase, we know that that's an exothermic process, right? The reaction is giving off heat, and so it's an exothermic reaction, right? The bubbles of gas evolved could be hydrogen, it could be anything else, any other gas, but we're gonna just say hydrogen for now based on what we know is happening. So if we have calcium is a solid, right? And that is reacting with distilled water in a container, chances are we're gonna get that the calcium is reacting with the water, and we're gonna get calcium hydroxide is a potential product there, and then we can get hydrogen gas as well, right? Because that's a metal there. So if we think of this equation as what's happening when we dissolve the calcium in distilled water, or put the calcium in distilled water, that we're getting a hydroxide of some sort and hydrogen gas, then the bubbles of gas would correlate to it being hydrogen gas, and the white suspension would correlate to being calcium hydroxide. And then if the temperature increased, then you know it's an exothermic process where the reaction is actually giving out heat, right? So the question 27 is saying that what would the gas evolve expect? The gas evolve would be expected to do what? So as we said, we're hypothesizing that the gas that gets evolved would be hydrogen, right? What does hydrogen do? Does hydrogen relight a glowing spin? No, it's oxygen that would do that, right? Does hydrogen decolorize acidified potassium permanganate? No. Does it give a pop with a lighted splint? Yes, that's true. So our answer is C here, okay? So what is true about hydrogen? What would hydrogen gas do? It would give a pop with a lighted splint, okay? So our answer for 27 is C. So moving along to 28 now. 28 is saying that calcium forms a white suspension. It's a suspension, right? That it's forming in water because what? The hydroxide is slightly soluble. Calcium hydroxide, that's true. Remember we said this earlier in the session that hydroxides are mostly, right, insoluble, but if it's calcium hydroxide, it will be slightly insoluble. And so if it's slightly insoluble, it's gonna dissolve to a small extent in water, and so we'll end up seeing a white suspension, right? So our answer here is in fact A, right? We're not forming carbonate. That's not what we're forming. We're forming a hydroxide, so that can't be right. We're not forming an oxide, so that can't be right. And we're not forming a sulfate, so that can't be right. We are in fact forming a hydroxide, and that hydroxide, calcium hydroxide, actually turns out to be slightly soluble in water. So our answer for 28 is A, right? So 29 says that a sample of this suspension that we made up here, right, is going to be filtered, and the pH of the filtrate will be determined, right? So if we filter our suspension, right, what's going to happen is that the filtrate, the liquid that passes through the filter paper, is what we're going to then measure the pH of that, right? So we're going to have our filtrate. So we have our filtrate here now that's in a conical flask or a beaker, and this is our filtrate, right? And that's from filtering the sparingly, the slightly soluble calcium hydroxide. So we have our filtrate that's now in a flask. We can use a pH probe to find the pH, right? So we're gonna put a pH probe in it to measure the pH, and then what would you expect that pH to be, right? So remember now in our filtrate, we're just filtering our calcium hydroxide, right? Suspension. So in the filtrate, we're gonna have calcium hydroxide, the soluble portions of it, right? And so because this is a base, we're gonna expect to have a basic pH. So this is not a basic pH, so A can be our answer. That's more acidic, right? This is also more acidic, a weak acid. This is neutral, 7 is neutral, so it can't be that. So the only thing that corresponds to our suspension or filtrate being a base would be a pH of 10. So we're going to get a pH of 10 then, right? When we measure the pH of the filter, we're going to get a pH of 10 because that corresponds to there being a base present, right? And we know that calcium hydroxide is a base, okay? All right, so moving down to 30 now. 30 says that the increase in temperature shows that, what does that show? So go back up top. Remember we said that the temperature increased when we had this reaction taking place. Temperature increase, and we said that that's correlated to the reaction being an exothermic one, right? So let's look at our answers here and see if anything matches up with that. So if the temperature increase, we said that it would correlate to it being an exothermic reaction, right? So in an exothermic reaction, then guys, is the increase in temperature correlates to the bonds in the product being formed? No, that's not true. Is the increase in temperature correspond to the bonds that are being broken? That's not true either. Is the increase in temperature corresponding to the products contain less energy than the reactants? That's true, right? Because remember now, for an exothermic reaction, right, delta H is negative, right? And so that's because remember that delta H is H of your products minus H of your reactants. That's what delta H is, right? So in order for delta H to be negative, which is the case for exothermic reaction, that means that your products actually have a less energy than your reactants. So if your products have an energy of, say, 100 and your reactants have an energy of, say, 500, right? Then you're going to get a negative number. You're going to get a negative 400, right? And because this is what's true for an exothermic reaction, then we can say, yeah, of course, the energy of the products will be less than the energy of the reactants. And so that's our answer here, right? That's what we have in an exothermic case, right? If from an energy profile diagram standpoint, right, that would be that we have our reactants down here, and then we go up, and then we come back all the way down. This is for our exothermic reaction, and again, this is our H of our reactants here, and then down here, right, would be the H of our products. And this is for exothermic reaction, energy profile diagram for exothermic reaction. So the energy of our products then is less than the energy of our reactants. And so that's C here, okay? So that's the first 30 questions here. Please remember to like, comment, subscribe to the channel, and I'll see you for part 2 of this, okay?